Okay, welcome everybody to the second seminar in this machine learning seminar series. Today we are very happy to have Josh Spiegel here, who will be giving our second seminar. Josh did his undergraduate here at Harvard, and now he's a graduate student. He has been working in astrostatistics and machine learning. He is in his second year, and today he will tell us a little bit more about how to use the different machine learning applications out there. Thank you.
Awesome. Thanks a lot, Cora. So, yeah, she mentioned I'm a second year in the astronomy department, and a lot of my research actually focuses on pretty much this exact picture. So last week, the speaker, Ashley, sort of talked a lot about how neural networks work, and she opened up with this meme about how machine learning sort of works from a statistical perspective and sort of in practice. And so Ashley sort of joked that, you know, she very much is in like the bottom camp, right? A lot of people fall in that camp. You have some complicated method like a neural network. You know, it's supposed to do things, you train it on data, and if it doesn't work, you just add more layers, and then somehow it magically improves. And this is the story of deep learning, which is all the rage now. I tend to come from the perspective more on the top, which is from a very statistical-oriented perspective. And for those of you who've interacted with me, can probably attest to my statistics, like sort of overly zealous approach to things. And so what I want to focus on today is a big complement to what Ashley talked about last time, which is about trying to understand machine learning from a little bit more of a statistics perspective, especially like a more Bayesian perspective on statistics, and to treat it much more like a toolkit that you can use to try and make inferences about different data sets using things you know. So to really take apart this mentality that it's this black box that just does magic, and really focus a lot on what are the assumptions that you're making, how do those assumptions translate into things that you're more familiar with, things like priors, things like likelihoods, and then I'll give you a bunch of examples of how to do this yourself in scikit-learn, which is designed to allow you to really hack at a bunch of different machine learning techniques very quickly and incorporate them into more complicated statistical models. And I've used it quite a lot. So for those of you who are interested, I will be going through, this is an interactive presentation, which means I'll actually be running code for you here, and I'll be demoing code. This is all in Python. If you are interested in grabbing this notebook for yourself, I actually have an earlier version of this uploaded on GitHub. So if you search my name, Josh Spiegel, on GitHub, you'll find this in the Harvard Machine Learning Journal Club group. So if you'd like to download this, run all this code yourself, I would highly encourage you to. And I have a bunch of sort of assisted text that you can then use to grab it yourself. So for anyone who wants, that's just, the repository is pretty much just up here. So GitHub, Harvard Astro _MLJC, and then sklearn demo. So before we get started, you just do the typical thing. So for this talk, I'm going to be adjusting a bunch of the basic utilities. So I'm a bad person, and I'm going to be essentially using this Pylab magic marker, so I don't have to type in any commands with NumPy in it. And I'm going to be increasing all the font sizes so that everyone can see. And since I'm using a specific random number seed, anyone who runs the exact same notebook should be guaranteed to get the exact same results. So you can compare these results with other things in the future. So to get started, I want to just get a quick show of hands. How many people are familiar with or have heard of like Bayes' theorem or have seen some form of this expression before? Perfect. Then this is the right talk. So typically, the way we think about Bayes' theorem is in the context of models and making inference. So typically, you have some parameters, theta, some data, d, and you're trying to combine those two to come up with a posterior based on your prior beliefs and the likelihood determined by fitting your data. So what I'd like to say is that machine learning can be thought to function in a very similar way, and this is a bit of an unorthodox way to talk about it. But you imagine that in the machine learning case, your prior is really your data, the training data you have that you're going to use to try and teach your algorithm what to do. And that data represents your current state of knowledge, the things you think you know about whatever you're studying and how it works. And so in this case, we're going to think about an object in the training data as being A, and we're trying to figure out the properties of an unknown object that I'm calling B. And so using sort of Bayes' theorem, you can write this out as just being, P of A given B. So the probability that, an object within your training data is a good match to an object that you don't know about, is just equivalent to the prior, this P of A, times the likelihood, this P of B given A. And if you're trying to then make inference about something that, is related to those, like let's say that we're interested in inferring something called Y. So Y could be anything. Let's say we're trying to infer something like redshift or other galaxy properties or some physics particle properties or some real world data like survey info or political affiliation. You could imagine that's some Y. So Y here is something like a label or a target that we're trying to predict to. And if you just go through the same Bayes' theorem logic, you can write it out sort of like this. And so this is just saying that all you're doing is you have this P of Y given A. This is just the label attached to any given object. So some training object A is going to have some value Y. And you're going to weight it by P of A given B. So the actual posterior that you derive from your training data. So this is a very abstract representation, but what it means fundamentally is that you can really think about machine learning from this perspective. So if you want to make a guess, like I have some unknown object, I want to figure out some property about it, I want to know where it is, what it does, you can sort of go through your training data, fit it somehow, come up with a likelihood score, assign some prior, and you can come up with a belief. The way that machine learning works here is that this is very abstract. And in general, you have no idea what your prior is or what your likelihood is, and in many cases, what that even means. Like if I give you two images and say, hey, how similar does this face look to this face? What does that likelihood look like? Very unclear how exactly that should be phrased, what exactly that means, and what exactly like the likelihood is as a concept. Can you actually quantify distances of faces from each other, in any concrete sense? And so what machine learning does is it gives you a handle on this by saying we don't know what the likelihood is, but we're going to parameterize it in terms of some assumptions for what is allowed. And those assumptions are the key that underlie almost every machine learning algorithm. Those assumptions are either a set of choices you make, saying that this object is or isn't similar to another object, some distance metric you pick, how close an object is, etc. And so those assumptions, the way that you allow that to be parameterized, gives you your likelihood.
I just wanted to ask a question about these basics, before we move on.
Right.
For many of us, as we move into the era of, let's say, LSST, you might think the data set is just a time series, for example, and then you have a kind of a neat formulation for that.
Mm-hmm.
In fact, though, if you just have the time series, you probably get very limited results in many cases. And what you really want is you want to look at a full range of other complementary data.
Mm-hmm.
So you might want to put it together with images, for example.
Mm-hmm.
You might want to put it together with some previous behavior that's been studied.
Mm-hmm.
And so rather than having data of one type, you have a melange of data of very different types.
Mm-hmm.
So my first question is just conceptual. Can all of this be done in the same way at this level? Or do are we in a kind of a different regime when we're trying to combine all of these different types of data?
So conceptually, I would say that it's the same. So the only thing is that, what exactly, the questions just become a little bit even more difficult about what exactly you mean when you talk about like what's a likelihood and what's a prior. But the concept of machine learning is to try and take those and, given some assumptions, try and essentially use the data to determine those yourself. And so even in the future where especially when you're combining and mixing and matching tons of different data types from many different data sets, I think this way of thinking about things is useful. Yeah. So the thing I'd also like to emphasize from that too is that the role of the prior in machine learning can be somewhat unclear, but this should be really thought about as your training data. And so your training data is going to serve as a prior for what your machine or what your algorithm is really learning. And so that means that if your data set is, for example, biased, if you know that you're missing objects or that you have certain objects where you have errors in the measurement, this will actually propagate to your results. And so that means that when you want to, say, reweight your data or fit populations that are a little bit different, that means you have to deal with modifying your training set, the same way that in sort of a Bayesian formulation, you often have to modify your prior. So that's just meant to frame conceptually what's going to happen here. But for the rest of this talk, I'm going to go through much more about thinking about what exactly it means, what exactly this likelihood means in the context of machine learning. So in general, machine learning can be broken into two different categories. The first is known as supervised learning, and that's essentially when we know something about our objects and we have a set of labels. So it's when we have these Ys and we observe a set of X's, and we're trying to predict something using that. So that's known as supervised learning. Unsupervised learning is when you're much broader. It's when you're not trying to predict something in particular, but you're much more looking to find patterns and doing sort of clustering and other type of recognition. And so in that case, you can really divide that into problems where you're looking for discrete groups versus problems where you're looking for more general structure. And so that is the main division in machine learning, is whether you have sort of these things you're trying to predict, or whether you're just sort of looking for patterns in the data. And each of those have some different approaches. So scikit-learn is really nice because it actually has a set of built-in data sets that you can use to test all these different properties. And so first, what we're going to do is we're just going to import both of those here, and we're going to focus on trying to put these concepts into practice using a bunch of example data sets that they have. So the first one is this data set known as Iris. And the idea here is that we're going to be given some data concerning some flowers, and we'd like to be able to classify them based on 4 observed properties. And so what we have here are essentially the length and width of the sepals and the length and width of the petals. And we're going to try and use these to classify our data into 3 different types of irises. And so just by running through this little snippet of code, we can print a description of our data set, and we've loaded it in to these 2 vectors known as iris X and iris Y that we can use for testing. So the first thing we're going to do is just to get a sense of what this looks like. So I'm just going to essentially mix up our data set, so we're just not looking at the same thing, and we're just going to take a look at breaking up our data set into a training set and a testing set. So again, the idea here, similar to what was talked about last week, is that we only want to use some of the data to actually train our algorithm, because we always need some data available to check how well we've done in the end. And this prevents against overfitting, where when you fit all of the data and you have nothing available to check, you might have actually fit for noise. And so that's just what I've done here, is I've separated into a training and testing data set. So one of the simplest sort of machine learning approaches, or what might be considered sort of a non-parametric approach, is known as k-nearest neighbors. And here, all we're just going to do is we're going to make an assumption that says, I bet an unknown object is probably similar to objects that look like it, which is probably fair. And so that's just going to say that we're going to look at the k nearest objects. We're sort of going to average them together. And we're going to say that this new object probably looks like the k objects that are closest to it. And so that's what we're going to do here. This is an example of how easy it is to code up an algorithm like this in scikit-learn. The first thing we're going to do is we're going to import this method. Then we're going to initialize it. We're going to fit it on our data. And then we will use the predict function to predict to our new data set. So what we've done here, this is the set of features that we've observed. This is the set of labels or targets that we're hoping to predict, and we're just going to predict it using this new set of stuff. So that's it. 4 lines of code, machine learning done, right? We can all go home.
Where's the metric that tells you what how points are close to each other?
Yes, that's initialized by default here. So there is a hidden metric under the hood, which is the biggest assumption that you make. Typically, that's the Euclidean distance metric. But there are loads of problems with just using that depending on the data. Yeah, I can see you shaking your head, so yes.
So if you wanted to change that, you would have to go inside one of these things that you're pulling out
That's right. So that's actually what I'll do next. So this is just showing if you run it out of the box, we do pretty well. It seems that we missed one. We misclassified one object. And if you take a look at the actual object itself, here is the k-nearest neighbors class. And so you can see there are tons of different options that you can specify within the context of our algorithm. So you can specify how you'd like it to train, what type of tree it's going to use, what type of distance metric it'll pick. You can specify specific metrics, how many neighbors you want, and then you can even specify the norm of your space if you don't like Euclidean distances and you'd like to work with some other type of geometry. And so that seems pretty straightforward. So we've made an assumption here about our petal data set. We don't know ultimately what we're assuming first, that all petals are similar to the petals that we just used in our training data. That seems fair, that we have some very representative sample of irises. And the second is that the simple Euclidean distance metric is probably a good way to determine how similar objects are. And so what we're going to look at is exactly here is now what this looks like. So this is now plotting what are known as decision boundaries. One of the biggest issues in machine learning is visualizing what exactly your algorithm is doing. So that's what I've tried to do here. So this is if we use only 2 of the 4 available features and we try and classify objects, what does that look like for our nearest neighbors algorithm? So you can see the 3 groups here are sort of this red, light green, and blue colors. The different shaded regions indicate, where our algorithm would classify an object as being one or the other. And so we can see that there's this nice division, at least in these 2 dimensions, between the red and the blue and green. And there seems to be a lot of mixing and matching over here. The reason that these places cross over each other is that at any given place, when you search for the 5 nearest objects, sometimes you end up with more blue objects than green, and sometimes with more green objects than blue. And so that's why you're sort of randomly switching around. So this, although the method is simple, this isn't necessarily what we might imagine we want from such an algorithm, right? This seems like these boundaries are really messy. There's not some clean set where you can say, if the petal length is greater than 5 and the petal width is less than 2, we classify it as this, right? It's much harder to interpret what exactly these boundaries mean. And so that leads to different assumptions. And so another method that actually is pretty common in statistics and other fields, but I haven't seen used as often in astronomy and physics, is something known as logistic regression. And I just want a quick hands for anyone who's heard of this method. Has anyone used this in their work? All right, we got one. So one person has used this. So the basic idea here is we're just going to come up with a decision boundary, and that boundary is going to be based on the logistic function. And so now we're going to put a harder constraint on our problem. We're no longer saying, okay, it's just what objects look similar to each other. We actually want to come up with a location, a boundary, where to the left of that boundary, or to one side, we're going to be in one class, and to another side, we're going to be in another class. And so that's what we're going to do here, is we're just going to use this function, the logistic function, and we're going to see how it goes. And so just like before, scikit-learn is designed to be extremely modular. So all I'm just going to do is I'm just going to initialize a logistic class instead, and I'm going to use the exact same code to train, test, and predict for these results. So in this case, we find that we actually are able to do better than before. We're able to do a one-to-one match. And as before, we have a bunch of hidden assumptions in this problem that you can reveal just by looking at this logistic class. So this C, for example, is essentially this fudge factor, so how wide or how fuzzy you want to make these boundaries. You can weight the classes to essentially account for some cases where some classes are biased, where you have many fewer objects in one than the other. You can fit for intercepts, you can scale, you can specify a bunch of things about how you train it, etc. And so just to show you what those look like now, this is what our new machine learning algorithm has done. And here we can see that this gives us something that seems much more clean. So we have this point, this sort of decision point in our 2D space at the center. And outwards from that, we essentially classify our space into 3 regions. And so this is, when it comes to classification, seems like a much easier metric to do. So again, these are the two assumptions we've made. In the first one, we just made an assumption that said objects are similar to their neighbors, where what exactly a neighbor means is something you have to put in. And this one, we've said objects to one side of several lines is in a particular class. We can do a little bit broader than this. Another type of classification algorithm is known as a support vector machine. And this essentially is just a broader way to come up with where these lines are located. So in logistic regression, you've assumed a particular form for how this function should take. In a support vector machine, you can essentially set up those boundaries to be much more flexible. You can put them, and they don't all have to agree at some particular point. So again, we can go through the same thing. Using the exact same 4 lines of code, we can import our support vector machine. And here, in the first case, we're going to use this kernel function, which is linear. This kernel is what allows a support vector machine to come up with more flexible parameterizations of the data. And it actually comes up very often in machine learning. And so kernels here are something that I want to come back to in just a little bit. So if we look at the exact same result here, we can plot, see how we're doing. And so under the linear kernel, we can see that now our decision boundaries don't all have to meet up at some point. They've shifted a little bit. So we've allowed a little bit of leeway in terms of where we place our objects. But we're still under the same assumption. We still assumed that there's some line we can draw and that objects to some side of the lines or another side are part of some group. And our likelihood is, of course, conditioned on that assumption. So one of the really cool things about support vector machines is they allow you to use these kernels to come up with more flexible parameterizations of these lines. And so in this case, we can use a polynomial, which says that maybe our line shouldn't just be straight, maybe they can curve. And so that's what we get there. This still is very intuitive. We've come up with some basic functional form for how we want these boundaries to behave. And now we have a little bit of a different view on what our algorithm has learned from our data set. Alternately, we can also use what are known as radial basis functions, which in any other field are called Gaussians. And you get something like this. So again, the key point here I want to emphasize are 2 things. The first is that if you notice our training data, it doesn't actually span most of the parameter space that I'm plotting here. And so depending on the assumptions we make, although we do a pretty good job in all 3 of these choices at classifying which objects belong to which category, the prediction outside of our training set can vary wildly. So you can see in some cases that the red region and blue regions here, for instance, what exactly you'd think about as you go to, say, very features that are way outside of our data set, say in this region over here. In the linear case, we'd assume that that is red or blue. Here we would think it's actually green, even though we have no objects there whatsoever. And so these assumptions, this is sort of trying to emphasize that really in machine learning, you only can make predictions to objects that look like things you've seen. That's the fundamental constraint here. And so what assumptions you pick really can affect how badly or how well you can extrapolate outside of your training data. And so these assumptions are really important and something that I think people should definitely focus on more when you're trying to apply this to your data set, especially if you know that your training set is limited in certain regions of parameter space.
Can you find training sets that are similar to other training sets? And let me give you an example so it doesn't sound like a crazy question. Suppose you are looking now at a large time series and you're not really sure what it means.
Mm-hmm.
So you pick your training set. Could you add a procedure where you now take a set of known types of variability and compare your training set to training sets you've used there? And, so in other words, that would have the effect of even though you couldn't do better than you just said here with the training set, when you get to regions that you haven't seen, if you now do this comparison to the other training set, which maybe covered some of those regions, you can now say, well, there's a probability that in your case, for example, it would have been green or it would have been blue, and it would be based on some information
So this isn't an open area of investigation. I mean, this usually, in like the language of machine learning, is known as data augmentation. So if you have other data that are similar but not the same, you'd like to use it to sort of broaden where you can apply your results. And so exactly how effective that is can vary a lot, and it's particular to the data set. But people do look into this, and there are also other ways to try and bake in assumptions so that your predictions are a little bit better at terms of extrapolating outside. One of the things that I focus on a lot and that I care about is physical models for your data. And a lot of what I work on is coming up with methods that are data-driven, more machine learning oriented, but whose sort of fundamental assumptions are very physical. And so that way, when you fit data and you go out and try and fit something else, you actually can extrapolate far beyond your training data. But again, that's all about putting in the right assumptions and thinking a lot about what your algorithm means and what you're trying to do here. So did anyone have any questions, by the way, before I move on from sort of the simple classification scheme to regression? Yes. Mm-hmm. Right. So that's like a very philosophical question. If you have sort of two machine learning methods that perform equally well on your data set, should you prefer one or the other? My feeling is generally to prefer models that are simpler and more physical, or at least more interpretable. So usually, like in this case, if you had a logistic regression model or a support vector machine model that performed identically on your data set, and you'd like to wondering which one to pick, I would generally go with logistic regression because it is simpler and more interpretable than the support vector machine. Mm-hmm. Right. I mean, that's the huge problem, is that you only can really evaluate your algorithm when you know the answer. And so when you're looking at your training data, a lot of people try their best, come up with very rigorous ways of doing training and validation and testing internally. But you're right, when you apply to your actual data set, it's very difficult to say which one is better. I mean, usually the two methods I think that are good ways to check if something has gone terribly wrong is whether first you get predictions that are far outside what your training data says. So if you apply your two methods to the data and one ends up returning a bunch of classes of objects that seem new, that were not in the data set, that usually should raise a red flag that somewhere you've extrapolated something dangerous. The second is some methods actually do allow you to compare essentially like a goodness of fit score. So like in the k-nearest neighbors case, you can actually say, what's the closest object to me? And you can then try and use that to say, look at your data and go, I don't have any neighbor within a reasonable distance of me, so this prediction is totally garbage. So in some cases, you actually can follow that through. In other methods, like neural networks, you can't do that at all. So it's really a method-specific question. Yes?
I guess cross-validation is another approach for determining models.
Right. But again, that's all internal to the training set. So you've always taken your training data and tried to divide it into some type of training, validation, and testing sets for your actual data. Does that answer your question? So I think you guys are all asking the right questions here, which is that unfortunately it is kind of hard to take a method that you've done here and extrapolate it elsewhere, which is why I think it's very important to consider all the assumptions that have gone into whatever machine learning algorithm you work. And this isn't like just meant to be hypothetical. Every couple days in the archive, I'll see X, we applied X machine learning method to do Y problem, and it does better than traditional method, but often there's not a discussion of why did this method do better, what are the assumptions that this method makes, et cetera. It's sort of just a focus on performance. And so lots of these issues that have come up are precisely related to the fact that, you should care a lot about what those are. So in this case, this is actually a very, close to home example. So this is a data set of Boston housing prices. Not anything current. It's a little bit out of date. But here what we have is about 506 housing prices and 13 attributes that we use to predict them. And so these include, the general crime rate, oxide, taxes, median value of the house, etc. And so we would like to use these to try and see if we can predict housing prices for these. And so this, if I remember correctly, is quite old. It's from 1980, if I remember correctly. And so let's take a look at exactly what this is. So for example, what we're just going to show here is just looking at two different things. Let me see if I can remember exactly what they are. RM is the average number of rooms per dwelling, and NOx is the nitric oxide concentrations. So for example, here's what we get for those two values. Those are two random things. You can see that they span a very wide range in actual stuff. And here is the median value of the house in thousands. And so, again, we see that there's a pretty broad spread. This spike here is because for some reason the data set peaks and it doesn't actually record houses that are more expensive than like 500,000, which I guess was a lot back then. Yeah, I mean, the housing prices today are even crazier. So the first thing that we're going to do is linear regression, and this will go directly into methods of validating your data using, as Lori mentioned, cross-validation. And so in this case, we're going to do the simplest machine learning method, and that's just linear regression. It's kind of a joke, but that actually is considered machine learning. So all we're going to do here is you're going to use scikit-learn to do this, and we're going to take from this model selection, we're going to import cross-validation prediction, and we're also going to import something called pre-processing. And what that does is try and resolve some of the issues that you instantly think about when doing things like k-nearest neighbors, where what if one parameter spans a much wider range than another, then that value will end up dominating when you consider whether something is close or not. And so what normally is done in machine learning is to standardize everything so that they all range from -1 to 1, and their means are all 0. So that's the idea, is that we want everything to have mean 0, standard deviation 1. And so that's what we're going to do here when we normalize our set of observations. After that, all we're going to do is using the linear regression class from linear models, we're just going to predict using cross-validation our results. And what this is doing is it's taking our training data set and splitting it into 10 chunks, and then it'll use 9 of those chunks to predict the final 10th, and then it swaps out and does it again, so that by the end, we've actually predicted values to all of our training data without ever cheating by looking at that data itself. So we've just sort of done this 9 to 1 swap every time, and we're going to use that and see how we do. So that's our regression case. Yes?
So is it useful to use like the mean of those 10 runs?
No. So what we've just done is we've taken our data set and split it into 10 groups, and then we use 9 of those groups to predict the 10th. And then we sort of take the 1 through 8th and the 10th group and then predict the 9th, and then et cetera.
Does that mean slightly different? So you predicted, that means you predicted every item.
Right.
But the model that you use to predict each one is like.
That's right. Yeah. So in practice, you can then combine these if you want to apply it to something else. You could try and do some type of average if you wanted to use, say, all 10 models. But for this case, we're just going to ignore that little wrinkle. So you can see fitting a line is actually not terrible. It's not the worst thing to do in this data set. So the measured value and the predicted value seem to agree with, up to the final point where you sort of lose a lot at the high end. So we can get a little bit of insight into what's going on by looking at our coefficients, which is one reason why I really like linear regression. And so this is just taking a look at our coefficients and sorting them so that we can see what seems to have the biggest impact on our prediction. And so the reason that I plotted NOx and RM is because actually in this analysis, we find that those are the two biggest predictors, which seems a little bit weird because I'd never heard of nitrous oxide before this analysis. So it seems bizarre that that is, about 6 times or 4 times as important as how many rooms are in a dwelling, which to me seems like it would be much more important. This raises the issue, of course, about what happens when you have correlated data. And this is a huge problem in machine learning because much of the assumptions you make don't really deal with correlated data in the way that you think about. And so when you try and figure out what your data is telling you, you have to really try and either extract the correlation out or explicitly use methods that take that into account. And one of the ones that does that is using what's called a random forest. And this is built on this thing called a decision tree. Yes?
Last section, you gave a cross-validation, just 10.
It was just arbitrary. We could definitely go for more. Do you have a preferred value? I can just run it now, so it's not. Yeah. So usually cross-validation for testing, for trying to validate your algorithm's performance is based on sort of a compromise between the amount of data that you're using and the amount of data that you're predicting to. And so usually it's just a computational thing. Ideally, what you'd like to do is to train using every object but one, and then predict the value of that one object, and then repeat for every single object in your training set. That would be the ideal test case, because that way you've used up every possible bit of data you have. But it's usually very computationally infeasible to do that. So that's sort of why we click 10, but we could easily do something like 100. I could run this with 100. And because linear regression is fast, you see that we do a little bit better, but not a ton. So that's just saying that the more objects we have in our training set, the better we're actually doing to predict our case. But there's no reason why you have to pick a certain number. You're right.
Would you worry about trimming the test set size?
Yes, you of course do. So ideally, again, the goal is to have as many, the more cross-validation folds, the better, because you want the training set to be as large as possible. So in this particular case, right, the test set variation is not an issue because you're predicting to every object individually and combining them all at the end. So you're not sort of doing this thing where you predict using 80% and test using 20, and if the 20% is very small, then you have all this noise that's come in. Because you're actually using the entire training set to do predictions here or to do testing, that's not as much of a concern. So as in like the variation you're going to get is the same variation that's intrinsic to your training data itself because you've used every single object in your training set to check. So.
I think my question is exactly related to this because, for a lot of things there are best practices.
Mm-hmm.
Like you say, well, you know that although you have choice, doing it this way has been established to be better.
Right.
It sounds as if in this case there's still a lot of experimentation. You don't really know, or maybe you do. Is there?
So in this, I mean.
That you should really choose to be the training set versus.
So in this particular case, I would say that there is like the optimal way is to do cross-validation with the entire training set except for one object. That's the closest you're going to get to using the whole data set. But of course, in practice, that is very infeasible. And so you're right that there's no general like best one where if you can't do that, how big should you make them? There are general metrics for how much you expect, variation to come in. If you only, for example, are using 50% of the trained data, you're not going to be as good as if you had used 80%. So what you can do, though, is you can test with different cross-validation sizes. In other words, with different sizes of your training set or how much data you use. And as you make that set bigger and bigger, you should see that your predictions, or at least the quality of your predictions, should asymptote. So at some point, they're just gonna be the same whether you use 60% or 70% of the data. And at that point, it's not as important. Yeah. But if you're just doing a single case of training or testing where you have like a holdout set that you don't touch and you only use once, then definitely the size of that is very important because you're going to end up with variation in your metrics. So if that set's tiny and you try and say how good you are, if you have 5 objects, it's very unreliable how much those predictions will actually be informative. Does that sort of answer your concerns, or we can talk more about it afterwards? So in this case, what we can do is we can go to another sort of one of these more like non-parametric approaches. And so all that decision tree is doing is it's trying to take your data set and divide it into a bunch of categories. It makes a bunch of decisions and says, I think objects that are, where this decision is true or this property is true has some value, and objects where that's not true have a different value. And it does this over and over again, hundreds of times, if not thousands, to construct this decision tree. And at the end, after having made many, many sort of true-false decisions, you then assume, okay, objects in this final category are very similar to each other, similar like the k-nearest neighbors approach. The forest part comes from the fact that you often do this many, many times. And so what I'm going to do in this case is we're going to use 100 different decision trees, and we're going to do the same thing we're going to predict based on our cross-validation. Here you can see that it's significantly slower than linear regression because we're having to train and test many, many more objects when we build our ensemble up. And so we can then take a look at our predicted values, and we see that it's unclear whether we really do that much better than linear regression in this case.
Can you instruct correlations?
So one thing that random forests do allow you to do is compare how important certain features are. So this is similar to the coefficients from our linear regression. And here we get something that looks a little different. And so our top two values now, if you look at nitrous oxide, is not important at all. The most important feature is RM and this LSTAT. And just to check, LSTAT is actually the percentage of lower status of the population, which is a nice euphemism for poor. So we can see that as you might expect, the two top things that contribute to housing prices are the number of rooms in the house and sort of the general area, which would correlate with your intuition. And so we see that in this case, we've done a little bit of a better job of dealing with this type of correlated structure when trying to interpret our data set. We can also do the exact thing that is mentioned before. We can try and compute some score that asks how well we're doing. And so for this, we're going to use the mean square error, and we're going to compare using a bit of a larger data set here. And so in this case, we're going to ask how well we do relative to mean square error under many, many different realizations or trials. So this is saying we're going to do all this training and testing and cross-validation a bunch of times. And we're going to see, what's the 16th, 50th, and 84 percentiles for how our mean square error goes. And we see that in general, while the linear regression random forest seem to perform comparably, on average, the random forest does quite a bit better than linear regression. And so relative to mean square error, it seems like a more robust algorithm for this particular data set. So this type of testing is important for figuring stuff like that out. Yes?
Is there a criterion where you say this is significantly better?
It's similar in many, sort of. It's the same with any, if you're comparing fits and you want to say, how is this fit really better than that fit? It all depends on what assumptions you've made. So in this case, we've, what I can say is that, the 1 sigma interval for the random forest prediction, the 84th percentile is less than the 50th percentile for the linear regression. And so that you might use to say, well, this is, substantially better or somewhat better. You can do the same type of tests you would do with chi-square to figure out whether that's actually better for your purposes. So just to sort of conclude is, I'm going to now go into a little bit more fun stuff. So this is all optional material. But I wanted to show that, machine learning doesn't have to deal with just these very simple cases. The assumptions you make can be much more abstract and much more sort of based on heuristics. And those can actually then be used to construct interesting predictors. So one case is something called isotonic regression. In this case, we're actually going to put in an additional assumption, not that just we're going to fit a line, but we're going to assume that whatever relationship we have has to increase monotonically. So this, for example, it could be really useful if your data set is something like this, where you know that over time it has to increase, but you've added in some random noise to the observations. So the blue are going to be what we observe, the black is the true relationship. And so we can use isotonic regression and compare that to a linear regression in a case where we want to put in this assumption. And you can see the difference in our predictors here. So the blue is when we just fit a line, and the red is when we fit our isotonic regression model. And we can see that 1 is a much better predictor of the data because we've put in the assumption that it has to increase monotonically. And so that means that, the goodness of fit changes a lot. Exactly what it means for a fit to be good is different here. So that essentially is most of what I hope to talk about. So I'm happy to take questions now, and if there's additional time, I can happy to demo some of the other cooler features available in scikit-learn that you can use, like kernel regression or Gaussian process stuff.
Here for Josh.
Yes. This one? Mm-hmm. Right. So part of the case here is that when I looked at the coefficients for our linear fit, I'm only actually looking at, I'm not actually checking about how they're correlated in this model, because I've only fit first order terms. I haven't allowed for any cross order terms to be correlated. And so by construction, I've assumed in our linear model that all our variables are independent. So that's one reason. If you wanted to then, if you looked at, say, the random forest case, and you're right, they are extremely different, and they give very different physical interpretations for what the data set says, that might be some intuition to go back and then put in those higher order terms so you can explore, if I allow this to be very correlated, will I then find that, say, like the nitric oxide levels correlate strongly with like LSTAT or some other parameters. And so really it's some other variable that's important here. But yeah, this is what I would do is this I think shows that it's usually good practice to test several different algorithms on your data before settling on one, and especially seeing if they give you similar interpretations. If they don't, that usually is a red flag that there's some property of your data that you need to think harder about. Mm-hmm. Right. Mm-hmm. So I think I'll answer that each of the questions in turn. So the metric for determining closeness here, especially for things like random forests, are always up for debate. And you do have several options to pick from. So generally in a classification problem or regression problem, you're picking usually like the mean square error version of what close means, which is implying that you're assuming that your data is normal. Or is Gaussian at some level, or at least that your noise is that way when you're fitting. You don't always have to make that assumption, but generally that is the metric that's used. So when you're training a random forest, generally the metric that's used to determine how good something is when you make a split, or how good your fit is using mean square error and variance. The same is often true for linear regression, which often again assumes sort of mean square error style metrics. So that is definitely not guaranteed to hold for your data, especially if you know that the noise is definitely not Gaussian. And so in those cases, you can try and experiment with other metrics that might be better. And if you actually have intuition as to the statistical basis for your noise, you can try and introduce that explicitly into your algorithm. So this is something that I personally have worked on, where if you know what the noise properties are, you can then go and code up some machine learning algorithm that functions just like a, say, decision tree or random forest, but uses slightly different distance metrics instead. For the second question, as for like determining these feature importances, it's very difficult to say whether you're, removing parameters that are not important. The common practice, as in with many machine, that's used by many practitioners of machine learning, is always just essentially repetition. So it's just fit a lot of, the idea is you have your training set, you just want to fit tons of models to it many, many times and tons of different algorithms if it's feasible to. And then using many, many different realizations, then say how often does something occur, how probable is this, and then for objects that are clearly, for features that are clearly extremely important, then to essentially take those and use those. So like in this particular case where I've used a random forest, I've actually determined the feature importances 100 times for each decision tree separately, and then what I've done at the end is actually add all those up. And so I've tried to average over possible noise inherent in the algorithm when determining what is important or not. So that's always something that is good to look into, is always if you run different approaches or run the same approach many times, that you should end up with very similar answers at the end. So that's a good way to ensure that you don't end up removing something that actually might be important. Yeah.
This is kind of a general question. So when Ashley was describing neural nets, it was really clear what makes a neural net a neural net.
Mm-hmm.
What you've been talking about here, just a lot of it just sounds like being very careful with how you try to understand a problem that deals with statistics. So some of the things that you've described, I was putting codes years ago, but I never would have thought of calling it machine learning.
Mm-hmm.
I would just say, well, I'm using nearest neighbors seem like a good way to approach this. So I wrote a code that used nearest neighbors and it was successful. What is it that makes it machine learning?
Yeah, I mean that the name is pretty much just means any code that uses training data to make a prediction. That's why something like linear regression works, is because your training data is just your X's and your Y's. You fit a model to it, and then you come up with a prediction. So that's why all these different methods fall under the moniker of machine learning, even though for some people they might go, well, I don't think k-nearest neighbors is machine learning. It's not as cool as neural networks or something like that.
I wasn't saying that. I was just trying to understand, how do you know you're doing machine learning?
Right.
I guess if you're relating it down to a training set.
Yeah, that's always the...
It really has something to do with the fact that your learning is rooted in the data.
That's right. That's the fundamental idea here. And so I think the takeaway point is that people have thought about all different types of ways to learn from the data. Tons of those methods are available in are publicly available in things like scikit-learn that you can use. And if you come up with your own, I think that this would be a good metric. Often you can then turn that into a machine learning algorithm as well. So I think you also had
Yeah, so also as machine learning, you can make better predictions. I like that, but many people don't care so much about the ability to make predictions, and they care more about learning something new about the data. So the feature importance that you have there, it's kind of a nice way to do that. You know that the number of are there other ways to extract the meaning from the data?
That's really, I mean, the issue is that it's a very algorithm specific question. So for some algorithms, the answer is yes. The way that it works is very contingent to extracting meaning out. So with k-nearest neighbors, for instance, you can trace back, which neighbors did I use to make this prediction? And you can attempt to use those to say, well, what ends up being predictive or what doesn't. For a neural network, you can't necessarily do that type of traceback. You can't go, why did it decide to pick this parameter over that parameter, or this specific feature is being more important than that feature. It's very difficult to trace that back to some, easy to understand interpretability method. So, I mean, I think the most, a really common way is actually to use random forests. They tend to be pretty good at this. So I think that's like the rule of thumb, is if you have a data set and you think that it's amenable to machine learning, is you run a random forest to do a feature importance analysis. But yeah, unfortunately, it's a very model specific endeavor, for better or for worse. So I tend to prefer models that precisely allow you to do that. That's a huge bias that I have, is to really prefer models that allow you to extract meaning from your data. But that also means that in some cases they're not as predictive as you'd like. Yeah.
What about chaos? I mean, chaos is something that many data sets exhibit, and it means that in terms of predictability, you must lose predictability,
Mm-hmm.
no matter how well you knew what was happening to begin with. Is machine learning also used in situations where you know that there's chaos?
Well, I'd say that it depends on, machine learning really leverages, depending on the method, the statistical properties of your data set. And so even if, individual things can be very chaotic, if there is some sense of, there is some patterns in the data that do exist, it's usually better to find that. That said, machine learning is notoriously bad at dealing with noisy data sets. So the lower signal to noise, whatever you're trying to predict or find is, the worse machine learning tends to do, and the scaling tends to be very, very large. And so in cases where you know that, say, your signal to noise is on average 1 or less than 1, machine learning is often, only as good as randomly picking stuff. So definitely in more chaotic situations, machine learning is not very adept. That is an active area of research, though. So definitely don't quote me on that forever. Cool.
Okay, so let's thank Josh for a very instructive talk. Let's thank Josh again. And we will be meeting again. The next seminar will be at the CFA. We will be alternating between CFA and physics, and we really encourage physics people to go to the CFA and CFA people to come to physics. We think that it can be really very constructive to bring different perspectives on different things that each of us are working on. We can all learn from each other. So we want to make this bridge more fluid. So see you next seminar, and thank you.
Thank you all for coming.
Thank you very much.
Yeah, sure. It was great.